Hello everybody, welcome to this next video. So here we will be talking about triangular forms. We have till now talked about Jordan canonical form. Okay, so let me write down in a sequence. So we have talked about diagonal forms. We have talked about Jordan canonical forms. They are also called Jordan normal forms. And we have also talked about rational canonical forms. So these are the things which we have talked about. So in this video we will be talking about triangular forms. So I would like to make a point that although you can skip triangular forms, because we will see that every Jordan canonical form is also triangular form, but for the sake of completeness we can do it here. So let us see what is a triangular form. Suppose you have a linear transformation T from V to V, or you have a matrix A of size say n cross n over the field, if you are working in the field F, over the field F, right? Then if there exists an invertible matrix P such that P inverse AP is equal to an upper triangular matrix, then you say that A is similar to a triangular form. A is similar to a triangular form, or you say that A has a triangular canonical form. And if you are talking about the linear transformation, then you have to do the same to the corresponding matrix representation of that linear transformation. Right, now we would like to know that when can you write the triangular form of matrix. So we have a theorem which tells you that when can you write the triangular form of a matrix. So the theorem says that let T from V to V be a linear operator whose characteristic polynomial factors into linear factors. It means that either you are working on the field of complex numbers, then all the polynomials will be factored into linear factors, and if you are working on the field of reals, it may not be true. So you have to see. So we are saying that if the characteristic polynomial is factored into linear factors, then there exists a basis of V with respect to which T has an upper triangular matrix representation, or you can say that T is triangularizable. Okay, so you see, same was the condition for Jordan canonical form also. So for Jordan canonical form also, we were saying that if the characteristic and the minimal polynomial, they are factored into the linear factors. So you should understand saying that characteristic polynomial is factored into linear factors and minimal polynomial is factored into linear factors. They are the same thing, because we already know that minimal polynomial and the characteristic polynomial, they have the same irreducible factors. Fine. Okay, so we are not going to prove this theorem, but we'll just do one problem to understand that what exactly is the difference between Jordan canonical form and triangular form, and how we can write the triangular form. Okay, so you see, first of all, you know that if you have a Jordan canonical form, so how does this look? You have a Jordan canonical form will be something like, say, 2 2 1 0. Let me just write something random: -3 -3 0 0 0 1 1 0. So clearly this is an upper triangular matrix. So Jordan canonical form is an upper triangular matrix. Okay, that you can see by definition. Therefore it is a triangular form also. But if you have this matrix, so every JCF is every Jordan canonical form is a triangular matrix also. But if you have a triangular matrix, if you have an upper triangular matrix, say you have this matrix 1 2 3 5 7 minus 1 0 0 0. So this is an upper triangular matrix. It is not in Jordan canonical form. It is not in Jordan canonical form. So can you see the difference? That if you write the Jordan canonical form, then you can say that this is my triangular form also. But if you have written a triangular form, it may or may not be a Jordan canonical form, right? Okay, so for example, if I write this 1 2 3 1 1 0 0 0 0, so I'm saying that this is my okay, just make these as zeros everywhere. So I'm saying that this is my upper triangular matrix. Indeed it is a diagonal matrix, but suppose I'm saying that this is an upper triangular matrix, then obviously this is also a Jordan form, because you can consider them as 1 cross 1 blocks. Or I can take another example, say 1 1 1. Okay, so here I have 2 1 2. Suppose this is my upper triangular form, and by chance this is also into a Jordan form. Okay, so we have every Jordan canonical form is a triangular matrix, but a triangular matrix or an upper triangular matrix may or may not be in a Jordan canonical form. Okay, so let us look at one problem. So you have here a problem. Question is, you are given a matrix 3 2 minus 1 minus 1 0 1 1 0 3, and you are working on the field of reals, and it is asked that write the triangular form. Write the corresponding triangular form if possible. Okay, so what you are going to do, you will be finding the characteristic polynomial first. So here you can see we already know that how to find the characteristic polynomial. You have to put determinant of a minus lambda I. So here if you do that what you will get, 3 minus lambda minus 1 1 2 minus lambda 0 minus 1 1 3 minus lambda. So this is, you can do the calculations, this is equal to minus lambda minus 2 cube. So here you can see that the characteristic polynomial is factored into linear factors. So it is a linear factor here, right? So we can see that characteristic polynomial is factored into linear factors. Okay, fine. So for sure we can write the triangular form. For sure we can write the triangular form. Okay, so now the question is how to write the triangular form. We have not done any theorem. For example, in Jordan canonical form and rational canonical form, I have told you a theorem where you have a way to write down your Jordan canonical form and rational canonical form. But here we don't have anything, or I have not told you how to write this. So, but before going to triangular form, we would like to check if we can write the diagonal form, because if you can write the diagonal form, that is a triangular form. So for that you need to check the geometric multiplicity of this eigenvalue. So here you can see that lambda equal to 2 is the only eigenvalue with algebraic multiplicity is equal to 3, because it is occurring as a root of the characteristic equation 3 times. So algebraic multiplicity is 3. So let us check the geometric multiplicity of lambda equal to 2. So for that you will just put lambda equal to 2 here. So you have the system of equations 1 minus 1 1, 2 minus 2 0, minus 1 1 1, and then you have x y z equals to 0 0 0. So now you are going to solve this system of equations. So you see here you are getting x minus y plus z equal to 0, and or you can just, you know what you can do, you can simplify it. You can do this, r2 goes to r2 minus 2 times r1, and you can do r3 goes to r3 plus r1. So if you are doing this, r2 goes to r2 minus 2 times r1, you will get 1 minus 1 1, and then you have 0 0 here, and you have a minus 2 here, 0 0 2 here, and then you have x y z equals to 0 0 0. Fine. From here you can clearly see that z is 0, and then you have x minus y plus z equal to 0. That gives you x is equal to y. So your eigenvector corresponding to the eigenvalue lambda equal to 2 looks like x comma y comma 0, which is equal to x comma 0, because x is equal to y. So this is x comma 1 comma 1 comma 0. So you have only one linearly independent eigenvector. So this is your eigenspace corresponding to the eigenvalue 2. So you can clearly see it is this eigenspace, which is x1 1 0, okay, is of dimension 1, therefore your geometric multiplicity is 1. Fine. So if the geometric multiplicity is 1, so AM is not equal to GM, therefore your matrix is not diagonalizable. Fine. Okay, so clearly this is triangularizable. And for how to find the triangular form, so what I can do is your characteristic polynomial del t is minus lambda minus 2 cube. First of all, I will find the minimal polynomial. So you see, minimal polynomial has three choices. Either it is lambda minus 2 or lambda minus 2 square or lambda minus 2 cube. So why the negative sign is not there? Because we know that we choose the minimal polynomial as the monic polynomial. Now you have to see which one of this is your minimal polynomial. For that you have to put your matrix here. So if I name my matrix as A, okay, so this is A. So you just check it and you can do it. A minus 2i, I have checked it, this is not equal to 0. And if I do this, A minus 2i square, that is A minus 2i, this is also not equal to 0. And this is A minus 2i cube. This obviously is 0 from the Cayley-Hamilton theorem also, that every polynomial satisfies its characteristic equation. So this is 0. So this is the minimal polynomial. So in this case, minimal polynomial is lambda minus 2 cube, which is same as the characteristic polynomial lambda minus 2 cube. Right? Now you know that obviously the negative sign does not make much sense. You can remove it from the characteristic polynomial also, or if you want to put it, you can put it also. There is no problem. Now you go to your Jordan canonical form thing. There we say that if you have characteristic polynomial as t minus lambda 1 raised to power n1, if your characteristic polynomial is t minus lambda 1 raised to power n1 and t minus lambda 2 raised to power n2, t minus lambda r raised to power nr, and your minimal polynomial is t minus lambda 1 raised to power m1, t minus lambda 2 power m2, and so on, t minus lambda raised to power mr, then your Jordan canonical form, in your Jordan canonical form there is at least one block of size m1 corresponding to lambda 1. Then in JCF corresponding to lambda 1, you have one Jordan block, at least you have at least one Jordan block of size m1, and all other blocks are of size less than or equal to m1. And in this case we have to have a block of size 3, and because total dimension is 3, so we will have only one block. So corresponding to A, the JCF is, you have to write a Jordan block of size 3 with 2's on the diagonal. So this is your Jordan block, right? So your A is similar to this matrix, so which is also your triangular form, Obviously this triangular form is not unique. Fine. So this is one way I told you that you can just write the Jordan canonical form, because anyway the condition for triangularizable is that the characteristic polynomials are factored into linear factors, and that is the condition for Jordan canonical form also. So it means that for sure you can write the Jordan canonical form, and that is nothing but your upper triangular matrix. So you can say that this is a triangular form. And if you want to purely write the triangular form, so I can tell you a way. What you can do is, so if you don't want that pure method of writing the triangular form, I don't know whether this word pure is correct or not, Pure means that we are not trying to write the Jordan canonical form. Instead, we are trying to write the triangular form actually, right? So that way is, again let me consider the matrix 3, 2, -1, 0, 1, and then we have 1, 0, 3. I saw that lambda is equal to t is the only eigenvalue, and the corresponding eigenvector which was linearly independent, you saw above we have obtained 1, 1, 0. So 1, 1, 0 here you see we have obtained this vector, this here 1, 1, 0. This is the only linearly independent eigenvector, right? Okay, fine. Only linearly independent eigenvector. So what I am looking for, this is my matrix A. I am looking for a matrix P such that P inverse AP is equal to an upper triangular matrix. Okay, so this is what I am looking for. So what I am going to do is, I know that this eigenvector will somehow play a role. Okay, so what I can do, I can choose, instead of P, I am just going for P1, where this is, if this is V1, I am writing this as my first column, and then I am choosing 2 more columns such that P1 is invertible. And I know that if I choose 2 columns which are in such a way that 3 columns are orthogonal, then P1 is invertible. So I am just choosing 1, -1, 0, 0, 0, 1. I am just trying to make this P1 invertible. So you may have a discussion that how I am choosing these 2 vectors. So I am just doing whatever is orthogonal to these things. Okay, these should be mutually orthogonal. So obviously these are not the unique vectors. You can write something else here. You can write 2, -2. Here also you can write 3. So this is your choice. You can write your own vectors. So I have chosen this as my P1, right? So there is a reason that I am choosing them to be orthogonal, so that it is easy for me to find out the inverse. And if I do P1 inverse A P1, so this is what I am going to get. You can do the calculations. 2, 3, half, 0, 1, half, 0, -2, 3. Right? Okay. Now you see, on the first I got 2. So I am happy with this part because I want an upper triangular matrix. So this part I am happy with. So this part is left. Right? Now you see, what I will do, I will consider this smaller part. I will call this matrix as B1. I will call this matrix as B1. Okay, 1, -2, half, 3. Now I will try to make it into an upper triangular matrix. So I will try to find out a matrix such that PB inverse B1, PB1 inverse B1 is equal to an upper triangular matrix. So again I will find out the eigenvalues here. So you can do that. You just find the eigenvalues. 1 minus lambda, half, -2, 3 minus lambda equals to, determinant equal to 0. That will give you lambda is equal to 2, 2. So 2 is an eigenvalue with multiplicity 2. And then you can find the corresponding eigenvector. So that will be -1 half, -2 1, xy equals to 0, 0. So that will give you y is equal to 2x. So my eigenvector, which is linearly independent, will be 1, 2. So 1, 2 is a linearly independent eigenvector. So what I can do is, I will write 1, 2, and another vector which I will choose will be an orthogonal to this vector. So I am choosing -2, 1, -2, 1. So you can see they are orthogonal. I am calling it as PV1. So if I do PV1 inverse B1 PB1, I will get this 2, 0, 5 by 2, 2. Okay. So now what I am going to do is, you had this, right? You call it as B. Okay. So if you have this PV1. So from here, what I am doing 1, 0, 0, 0, 0, PV1 here, and my matrix B here. B was this matrix 2, 3, half, 0, 0, and here you had B1 into, okay, and we are talking about inverse, and then we have 1, 0, 0, 0, 0, PV1. Fine. So now you do this. This is what you will get. You'll get 3 2, 3, half, 0, 0, and here you will get PV1 inverse B1 PV1. Now this matrix here is this, right? So you get 2, 3, half, 0, 0, 2, 5 by 2, 0, 2. Now you call this matrix as P2. So this is P2 inverse B, and this is your P2 equals to this. And what is your B? B is P1 inverse AP1. So you get P2 inverse P1 inverse AP1 P2 equals to 2, 3, half, 0, 2, 5 by 2, 0, 0, 2. Now you see here you get an upper triangular matrix. Okay, and here what you can do, you can call this P1 P2 as P. So you get, okay, you get a matrix P. P is P1 P2, and you can do the computation. You just multiply P1 and P2, so you'll get this. This is the required matrix. Although we are not interested in this matrix, this is not even unique, right? And for that matter, this is also not unique, right? So you can get your U, which is the upper triangular matrix, similar to your given matrix. Okay, so this is also the triangular form. You see, before that what I have got this as my triangular form, and that was easier because I just used the Jordan canonical form. So this is also a triangular form. This is also a triangular form. There are so many triangular forms which you can find out. Okay, thank you. Please share this video.